Hello, guys. Hello, few guys apparently today. Are you doing well with the exam? Are you close to finish? How have you found the exam? Was it very difficult? Too easy? Not interesting enough? All right. Okay. You do have poker faces already, so we have improvement, I hope. Yes, and the feedback will be, especially when you talk about this thing. You see, guys, I will give you the exam, I'll grade it, and we can discuss the questions. I will probably not write too many comments. So I'll just say right, wrong, and just a few things that I will say about it. But we can discuss how I solve it if you're interested in, after class or before class. If you cannot make it, we can arrange a time. It's due Wednesday at midnight. I mean, I'm not going to be overly strict if you are late with it, but it would be nice if you, of course, can submit it by midnight on Wednesday. And you know that you submitted through my email, correct? Yes, I still receive people asking me. People ask me those questions. I just want to be sure that you get it. All right. Yes, I don't know what the others decided to do. It's a bit sad that they're not here, but let's get on with the lecture and maybe others will join. Of course, turn your cameras, guys, so that I don't feel that I'm doing a terrible job and that's why you're not here. So before I return to the topic of last Wednesday, let's briefly discuss some properties of cumulative distributions. And first, I want to say that probability is an increasing function in the sense that if you have an increasing sequence of sets, E1, E2, all the way to En and onwards, where E is the union of all those events, then the probability of E is the limit as n goes to infinity of the probability of En. And we can see that this is true by looking at the following onion diagram. So you can see E1 is this region, E2 is the bigger circle, and E3 is even bigger circle. No trouble, Maria, it's very nice that you made it. That's sweet enough of you to join. I cannot ask for anything more. So here are those onions. And as you can see, I can describe them as rings. You see, instead of taking the union of this disk together with E2 disk together with the E3 disk, I can take the E1 disk together with the annulus F2 together with the annulus F3 and onwards. And those are disjoint, as you can see, right? Those events are disjoint. So that means that the union from N1 to capital N of En is the same as the unions of the corresponding Fn. Annulus is a ring, if you don't know. So yes, it's a ring. Right? My research actually relates to those things. I can show you that later. It's very horrible, scary, right? And what I prove is tremendously gross. I don't even want to tell you what I prove. I mean, you would be nauseous. But it relates to annulus or annuli. So we have this region and this region, and altogether the disjoint regions produce the same thing as the union of En, right? And that means that the probability of E, which is the infinite union of En, can be written as the infinite union of disjoint regions Fn, and they in turn can be written as Riemann sum. I mean, not Riemann sum, just infinite series, right? Here we have it. and this is to be interpreted as limit as capital N goes to infinity of the partial sum. And now the partial sum can be brought back to the union, and that union is again the union of the En. And then you see that what is this? This is just E capital N. So we see that this limit is indeed true. That that the probability of E equals to the probability of the En. I hope you understood this explanation. And then, of course, we have a second lemma, and that tells us that if we have a decreasing sequence, then it's also true. The limit will be the limit of E. The probability of E, sorry, is the limit of the En, where E is now the intersection. Now we can simply rely on the previous lemma. We can just say that E complement is equal to the union of the En complement, right? And now E complement is now written as the increasing sequence of nested sets. Yes? And by lemma 1, we know that the probability of E complement is then the probability of En complement. But we know that the probability of a complement is simply 1 minus the probability of En. And so we have that 1 minus probability E is equal to 1 minus limit, as it goes to infinity, probability of En. And we can just cross out 1 and multiply by minus 1, and we get the desired result. So then recall what is a cumulative distribution. If X is a random variable, then we have this function capital F of X, and its meaning is that when I place a number B in it, I'm calculating the probability that X is smaller than or equal to B. Good? So it's how likely is X to produce a value at B or below B. And then you have the following observations you can make. First observation is that if A is smaller than B, then the cumulative distribution at A will be less than or equal to the cumulative distribution at B. And this follows instantly because if X is smaller than A, that's a subset of X smaller than or equal to B. Right? So the bigger the set, the bigger is the potential probability. So second part is that limit as B goes to infinity will equal to 1. And why is that? Well, we can use lemma 1. We can see that I can write E capital N, which is X less than or equal to N. And then obviously E1 is subset of E2 and onwards. And as I increase capital N to infinity, I will cover all of R. And then that means that by lemma 1, probability of R is 1, which is the limit of the probability En. But those are Fx of N. This is the cumulative distribution at N. So we can see that the limit of the cumulative distribution does indeed go to 1. You're following me, guys? It's a slightly boring lecture for a bit, about 8 pages, and then we do the very interesting stuff, but just we have to cover it. Similarly, if I go in the other direction, yes, right, I think the same way exactly of this particular thing. I hope to be over with this as fast as possible. As B goes to minus infinity, the limit will be 0. So En is then I can pick En to be X less than or equal to minus N, right? And then of course E1 is going to be a subset, or is going to contain E2 and onwards. You can see that as I go to increase N, I make E smaller set. E is like the interval from minus infinity to that minus N number. And right, so I'm kind of moving this way. And I'm allowing fewer and fewer values to be within the set E, right? And so what do we get? We get by lemma 2 that the probability of the empty set, which is the intersection of all those events, it's 0. And that's equal to the probability of En, which is the limit of the cumulative distribution. 0 is the probability of empty space or empty set vary, right? So it's over here. It's just, you see that the intersection of all those sets will be the empty set, and they are decreasing sets. So well, that's what we have, and this is why a cumulative distribution is important. I mean, I don't truly see why it's important for discrete random variables, which we're studying now, but it's very, very useful in continuous cases. We will see later, right? But here is the situation. So in theory, at least, all questions about probability can be retrieved from the cumulative distribution. In other words, if I know the cumulative distribution, I can solve all kinds of probability questions, right? So assume that I know the cumulative distribution, capital F function for x, and I want to calculate the probability that x falls between A and B with the allowance that x can equal to B. Yes, what can I do then? Well, I can write this as the probability of x less than or equal to B minus x less than or equal to A. So that means the intersection of x less than B and the complement of x less than or equal to A. That's what the minus means if you know set notation, yes? So what is that probability? Here it is. It's the probability of x being less than B minus the probability that x is less than B and x is less than A. But this is the same thing as probability x less than A, because this is the smaller set. You agree? This intersection, just if x is less than 5 and x is less than 1, then x is simply less than 1. And that's what I have over here. And that's the difference between cumulative distribution at B minus cumulative distribution at A. You will see that it will relate to the fundamental theorem of calculus. It's like the integral. When you integrate a function, little f, you get capital F of B minus capital F of A for the bounds of the integral. Yes? So this is why you have the situation. You have it not only when you deal with integrals, you also have it when you deal with discrete probabilities. Integration is just summation, and here we are summing up probabilities. So what about this situation, guys? Suppose we want to know what's the probability that x is less than b. Notice there is not less than or equal to, right? So what do? Well, if I have my cumulative distribution, I simply take x less than or equal to b minus 1 over n, and I push n to infinity. Because what do I create here? I create a sequence of increasing sets, and they increase, so E1, E2, E3, they increase to the set x less than b, right? And what I get is this limit. And in theory, I can evaluate it. So let's look at an example, guys, and you will help me figure out probabilities, okay? So here is a cumulative distribution. And I want to calculate the probability that x is less than 2 from that information. It has to be a number either, right? So if it's a probability, it must be just a number between 0 and 1. X is just, well, it's a symbol. Okay. How do I calculate x less than 2? Well, this cumulative distribution function means this tells you how to read when the probability for the probability that this random variable is less than or equal to the particular number over here. Good. So what do? So where do we look? We look here at 2. You see, we need that. We see at 2. So we see that if x is less than or equal to 2, we have if x is less than 2, we have that only 2/3 is what accumulates. But here we have x bigger than or equal to 2. So we need to look at values around 2. So we have 11 over 12 and 2 over 3. Yes? You see 11 over 12 and 2 over 3. Now, you see what I'm trying to convert this expression for. I want x, I mean, I can read x less than or equal to 2. X less than or equal to 2, it will give me 11 over 12, right? So if I plug in here x equal to 2, that would give me probability capital X less than or equal to 2. That will give me 11 over 12. But here I am asking for probability of x being strictly smaller than 2. So we're involved with numbers around 2. You can see here. Here we see x relating to 2, and here we see x relating to 2. So what do? We use like the previous limit. We take limit where x is less than or equal to 2 minus 1 over n. Right, slightly less than 2, and we will push n to infinity. You agree? Here is that calculation. I think I switched here to 3. Maybe I made a mistake here, right? Because I suddenly switched to 3. But the idea is similar. So we switch. If here we have x less than 2, then what do? So we have x approaching to 2, and we actually get 2/3. We just are in this case constantly at 2/3. Yes. You follow, guys, how I calculated it? Or are you confused? So the answer is 2/3 here. And why? Because if I instead here, what do? I don't touch 2. I look at limit where x goes to 2 from below of capital Fx. Yes. And what do I see here? If x goes to 2 from below, then I see the number 2/3. Okay, it's very important to understand how to do that. Yes, guys? That's why we had those two lemmas. We know that I can approach a probability of some event by writing it as a union of growing sets. Right? Yes? So I have E1, E2, E3. I mean, I can expand until I reach the set E. And the probability of E is the limit of the probabilities of those sets. Good. So you all understand how I got 2/3 here, yes? All right, I want to check. You are going to now help me calculate probability x equal 1. Could you do that? You see at this table, I want you to tell me what's the probability that x is 1. So that you don't lose track of it, I'll write it here on the board. I want probability that x equal to 1, please. Yeah, on the table you have less than or equal to 1, so so correct, that relates to it, but we have to be careful, okay? So see if you can get probability that x equals to 1. I see one answer already. Yes, Chiaran, that's kind of right. But minus what? Well, what is x minus 2, over 2? That means that this is just telling you how to use the formula. So if x is 1/2, you have 1/2 over 2, right? So the probability that capital X is less than 1/2 is 1/4. The probability that capital X is less than 1/4 is 1/8. That's how you interpret it, yes? And Maxine, yes, you are correct. Maxine has the right solution. It's 2/3 minus 1/2. Let's understand why. You see, guys, what happens here? Yes, if that's 2/3 minus 1/2, if it's 1/6, then that's right. So let's see it. So probability x equal to 1 is the same as the probability that x is less than or equal to 1 minus the probability that x is strictly less than 1. Do you agree? So you take x less than or equal to 1 and remove all probabilities corresponding to values that are strictly less than 1. Now, how do I calculate this? This is easy. This is the cumulative distribution evaluated at 1. And if you evaluate it at 1, it's equal to 2/3. Yes, you see that over here. When x is equal to 1, the probability is 2/3. It doesn't update until I jump over 2. Good. And then what then? And then we subtract the limit as n goes to infinity of the cumulative distribution at values that are approaching 1. So I wrote it, I just wanted to, the reason I wrote 1 minus 1 over n, you can just say x approaches from the left. I did 1 minus 1 over n to indicate how the sets are growing, right? We described it sequentially. So what do we get? We have 2/3 minus this limit, and this limit is 1/2, so it's 2/3 minus 1/2, and the answer is 1/6. Okay.
I have a question.
Yes, go ahead.
So it seems that if we're doing the limit of 1 over n going to an infinity, that's always going to basically go to 0, right?
No, if it's 1 over n, yes, it goes to 0.
Okay, there's other cases where it's different than 1 over n, I'm guessing.
No, I mean, all you're doing is, you see, if you understood the two lemmas, right? We described, it's called nested sequence of sets, right? So we have sets that grow and sets that decrease. And they decrease or grow, they are indexed by an integer, at least in the way we proved it in lemma 1 and lemma 2. So that's why I wrote the set this way. I mean, I can write, they do that a lot in real analysis. You write sets as countable unions of increasing sets or countable intersections of decreasing sets and all that type, right? So probability is behaving very well when you have that type of construction.
Okay.
Right. So I just try to describe the set x less than 1 as a sequence of increasing sets, right? So x less than or equal to 1 minus 1/2, x less than or equal to 1 minus 1/3. You see, so those are larger sets because I subtract less from 1/2. So I subtract less from 1, and the sets will grow. And then I want you to calculate probability that x is bigger than 1/2. Can you do that? Here is the distribution, and I want probability that x is bigger than 1/2. Oh, Camille, nice of you to come. Okay, Chiara, thank you. Looks good. Looks good. You see, you have two things that you want to do, Reader. Is that you want to convert it into expressions involving probability capital X less than or equal to some value. That's the cumulative distribution, right? No trouble, Camille. So you must be all from the same class, right? So I assume 10 of my students or so are from the same class. What is that class?
Yeah, vector analysis, Professor. It's been an issue. My internet is working slower. Like I couldn't.
No worries. I'm glad you came. It's no trouble. Yes, I just got jealous. I thought the exam was so hard that you forgot your name. Right? Yes.
No, Professor.
All right, are we ready, guys? So how do you solve x bigger than 1/2? Well, you want to convert it, right? The probability that x is bigger than 1/2 is the same as 1 minus the probability that x is less than or equal to 1/2, right? So that's 1 minus the cumulative distribution at 1/2. And we're told at numbers between 0 and 1 to just divide them by 2 to obtain the probability, yes? So the answer is simply 1 minus 1/2 over 2 or 3/4. All right, a little bit more, guys, and we're almost done. So what about this probability that x is between 2, strictly bigger than 2 and less than or equal to 4? Here is this thing. This is just so that you don't have to look there. Probability, I said x is bigger than 2 and less than or equal to 4, yes? What do we get? Okay. You ready, guys? Nick, you ready? Okay. So how do we solve that? Well, we simply notice this is the probability that x is less than or equal to 4 intersected with the probability that x is not less than or equal to 2. Right? X is bigger than 2, not less than or equal to 2. So that's the complement. Good. So this is the intersection of two events, and the probability is the probability that x is less than or equal to 4 minus the probability of x less than 4 or equal to it and x less than 2 or equal to it. Now the intersection of those two events is simply x less than or equal to 2. And so we have the cumulative distribution at 4 minus the cumulative distribution at 2. Right? And then I just read it from the table. The cumulative distribution at 4 is 1, and the cumulative distribution at 2 is 11 over 12. And I get the answer is 1 over 12. Very good, Barry. Congratulations. Now, what else do we have? And now we can finally return to interesting things. Good. So that was just a short segue. And now let's talk about expected value again. So we all remember what is a random variable. Yes, guys, I kind of used it here implicitly, but we all remember what a random variable is. Would anybody like to remind me? If you had to explain to someone what is a random variable, you would do what? All right, I guess I will try. And not any outcome from a sample space, no, vague, which is multiple outcomes across different universes, vague. Okay, let me try to remind you what it is, guys. So the word random variable is just a fancy word for tag, right? So you have a sample space, and the outcomes I labeled here are 1 through 7. For instance, it could be infinitely many outcomes, it could be finitely many outcomes, but the point is those are the possible universes that can occur once once you play the experiment, right? When I throw a coin, I presume there are two possible universes that can occur, either the universe with heads or the universe with tails, right? Everything else controlled for. Good. Now, this illustration shows you what happens if you play Russian roulette with a pistol. And you see, the outcome can be barrel 1, barrel 2, all the way to barrel 7. Those are the actual universes, the actual outcomes. But the random variable of interest to me is bullet or no bullet, for instance. Yes? So what is a random variable doing? A random variable, as you can see, those are tags. You see, there is a red tag saying bullet, and there are blue tags and 6 blue tags with the same label saying no bullet. Yes? So you can think of a random variable in two ways. First way, it's just a relabeling of the universes, right? And that might mean that several universes might receive the same label, right? Several different universes could receive the same label, as, for instance, chamber 2, 3, 4, 5, 6, and 7 receive the label N, and only one universe receives the label B. Yes? Now, what's the probability of N? To ask what's the probability of N is to ask for the probabilities of universe 2, 3, 4. It's the same thing, right? But now I see the probability is 6/7. Why? Because when universe 2 is occurring, I see N. If universe 3 is occurring, I see N. You see, the label is masking the actual outcome on the universe. Is that clear? So a random variable is just a relabeling from a sample space S. And in terms of functional definition, it's just a function from set S onto some set S star, nothing more. And the reason you call it random variable is because once you simulate the sample space S, that will induce a sample space S star, because any one outcome that happens in the sample space will be a random outcome. And then I will see either the tag B or the tag N. Yes, in this particular example. So the randomness in the random variable does not come from the labeling. It comes from the actual universes occurring at some random events. Good? Make sense, guys? Good. And what else? So we did some, we measured probabilities, right? So how do you measure the probability that a random variable equals some particular value? Usually the values you like to assign are numbers or vectors in some cases. In our class, it will be mostly numbers, mostly real numbers. Yes? So what's the probability that X equals to the probability of Y? That means X is giving you the label Y. That's the same as the probability that any universe that has a particular tag occurs, right? So that's what this weird notation is doing. P of Y is probability X inverse Y, and that's the summation of all the probabilities of all outcomes in S that produce Y. Right? All I'm saying is this, right? What's the probability of this situation? Well, that's the probability that any one of the universes carrying the tag N occurs. Is that clear? Right? So it's just because they were labeled. So now I might see N through many universes, not through just one universe. Like here we have universe 1, 2, 3. They were distinguished and distinct, and now with the label they are no longer distinct for our purposes. Okay, and we did a few examples, right, guys? So for instance, here is an example of relabeling universes. We had 3 balls that were randomly selected with replacement. The balls were numbered 1 through 20. We select 3, right? And the question is, what's the probability that that the largest ball that's chosen is larger than 17 or equal to 17? Yes. So I could solve this question obviously directly. It's not a hard question, right? But I could as well, I might as well relabel my my universes, right? So what are my universes? How many universes do I have here? Well, 20 choose 3 universes. Do you agree? Because each universe corresponds to the actual balls that were selected. So when I select 3 balls, I can present them to you. I show you which balls were picked in order. This is the smallest, this is the next, this is the next, right? I can present 3 balls to you that were selected. So there are 20 choose 3 universes for any collection of balls, right? Now, the X here, what does it do? It relabels universes based on the largest ball in the sample. Do you see that? So when I see 17 occurring, that means that that corresponds to any universe in which the largest ball is 17. If I see 18 occurring, that means the largest ball is 18. Yes? So you can see that the relabeling is not one-to-one. There are many universes that have the same label with this random variable, right? So the question is, what's the probability that the largest ball picked is bigger than or equal to 17? It means that what's the probability that the label 17 or 18 or 19 or 20 comes out? Yes? And then what's the probability that X equals to 17? Well, it's 16 choose 2 universes. Do you see why it's 16 choose 2 universes? Because we know in all those universes, the largest number is 17. And that leaves us 16 choices. So from 1 to 16 for the remaining 2 balls. So that's why it's 16 choose 2. That's how many universes are labeled as 17. 17 choose 2 is the number of universes labeled as 18, and so on. 19 choose 2 is the number of universes labeled as 20. Is that clear? So when somebody asks you what's a random variable, the first word that should jump to your mind is label, right? And that's the probability.
Is it choose 2 because we don't care what the third ball is? Just that.
No, we know what the, be careful. We know what the third ball is, right? So for instance, 16 choose 2, that's, I know that the third ball is 17 and I know my sample contains 3 of them. So if the third ball is 17, what are the previous 2?
Oh, okay. So the 2 are the balls that are not the higher number.
Right. The 2 are the balls that are not the higher number, and they must be chosen from lower denominations than 17. That's why it's 16 choose 2.
And
Right?
then the general universe is how many ways to choose 3 balls out of 20.
Yes, yes. And then we just relabeled a bunch of them. We now, from the perspective of this random variable, there are 16 choose 2 universes that look to us the same, and additional 17 choose 2 universes that look to us the same. Right? We just grouped a bunch of them based on the label. The label makes them identical for us. It's kind of like wearing masks, right? So if you go on Halloween and you wear masks, you might look identical to another person, even though you're a different creature, right? So then we here's another example. I'm just reviewing it. Hopefully that helps. So imagine that we toss a fair die until it comes out to be 6. Right? So the game is to toss a fair die until you see the number 6. And then the universes are what? Universes are, you know, 1 toss and then you get 6, or 2 tosses and you get 6 on the second toss and not on the first, right? And so on, right? There are many universes here. But I can label those universes 1, 2, 3, 4. I can just label them. In this case, the labeling is in... well, it's not in one-to-one correspondence. How many universes are labeled as 1? Right? Only 1 universe is labeled as 1, because that means that on first throw I have I rolled out a 6, right? How many universes are labeled as 2? Well, 5 universes are labeled as 2. Do you see why? Because the last number is a 6, and the first number is 1 through 5, possibly, right? And in general, how many universes are labeled as n? 5 to the power of n minus 1, right? Because if x is equal to n, that means that I'm looking at universes in which I had to toss my die n times, and n minus 1 of those tosses I did not get a 6, and on the last toss I got a 6. Yes. So that's so then what's the probability that x equals to n? Well, you can calculate it, right? So if x is equal to n, that means what? That means that the first was a failure. We can use independence here, right? So we can use intersection of events. First is a failure, so it's 5/6 probability times second is a failure, 5/6 onwards, 5/6 to the n minus 1 times 1/6. Yes, that's the probability that x equals to n. Good. And then the probability that x is going to be an integer, that means the probability that this game is going to end is the summation from n1 to infinity of 5/6 to the power of n minus 1 times 1/6. And you can see it's 1, which means that the probability that I have to toss infinitely many times is 0. That means it's very, very rare. You're not going to see that. Okay. Okay, discrete random variables, we mentioned what those things are. Yes, guys, if you studied analysis, if you know what is countable infinity or finite numbers, discrete random variables are random variables that take on either finitely many values or countably many values. That means you can order those values that x takes as first, second, third, fourth. You can put them in a queue line, so to speak, right? You can pair them with integers. So then we spoke about this labeling, right? So fair coin is tossed 2 times. Let x be the number of heads obtained. So, right, so we have 3 labels: label 0, label 1, and label 2. Actually, 4 universes, right? So exactly 1 universe is labeled as 0. That's when I have 2 tails. Exactly 2 universes are labeled as 1. Tails heads or heads tails. And exactly 1 universe is labeled as 2. That's head. And you can see the probabilities of each. Good? Makes sense, yes? So 1/4, 2/4, and 1/4. And we solved this question. I hope you remember it, guys. You know that the probability that a random variable takes one of its labels is 1. I agree, because when you run the experiment, each element in the sample space was labeled by one of the possible labels that x offers for us. Yes, and so the probability that x takes one of those labels has to be 1, because as soon as one outcome appears, it will come up with one of the labels. Right, and that is useful in solving this question. We already did this. Anyone needs to repeat it, or just to be sure? I'm not sure if you remember it, understood it. Do you need me to repeat it, or I may move on? Write Y for moving on, and write R for repeat.
Can you just go over what gamma represents?
It will be. We will say much more about it, right? But gamma represents. It's going to be a Poisson random variable, so we are going to actually later see what it all represents. Right now, it's like an abstract question where, for some reason, the probability that the outcome is n is given by this formula, where this is a definite number. Maybe gamma is 2 or 1.5. It can be any positive real number. Yes, and c is a constant that I don't know. C is a constant that I don't know, and I want to calculate what is the probability that x is 0. Now, the probability that x is 0, before I can calculate it, I need to find out what is C. Yes, and then what do I know? I know that the summation of all the probabilities has to give me 1. You see, so the summation gives me 1. I can factor out the C, and what is the summation? The summation is e to the lambda. So that means that C has to be e to the minus lambda. You all understand, yes? You see how I figured out that C has to be equal to 1, yes? Sorry, C has to be equal to e to the minus lambda, not to 1. Good, and then I want to know what's the probability that x is bigger than, well, x equal to 0. It's just, I plug in 0 for the formula, and I have the C, so it's this number. And the probability that x is bigger than 2, it's 1 minus the probability x less than or equal to 2, which means 1 minus the probability of 0 and the probability of 1. And I just plug in the numbers and I obtain this expression. Now, don't worry about understanding the significance of this random variable. This will be done later. It's a very, very significant type of random variable, but we haven't reached it there. Right, and here again, right, so I mentioned what is cumulative distribution. That's where we defined it. We just spoke about cumulative distribution and we drew it and we saw more properties of cumulative distributions. Yes, you all understand cumulative distribution is just the function less than or equal to some number. Again, I would have never thought of cumulative distributions and their need in the context of discrete random variables, but if you do continuous random variables, you will see that those ideas are right away useful and natural. And then, guys, we defined expected value. And this is, I mean, I labored and toiled writing that document and rotated that wheel millions of times. Did you understand what happened there? Do you understand what is expected value and the formulas to calculate it? And you have to understand, you will have to understand it very deeply. Yes? So the expected value is defined as follows. We'll check. And if you have questions, we will try to address those. So imagine that we have a random variable x, and that represents basically we have a game, and the game has different outcomes, just like the wheel of fortune has, let's say in our case, 5 different outcomes. There, you know, wheel of fortune. You know the actual the game, the roulette, right? Anybody has anyone ever played the roulette? I should make you read Dostoevsky's Gambler, right? So, and then you can figure out what you can win or what you can lose. It's very similar. I just made fewer sections, right? And you can see what sort of things you can, yes, 0, green, and etc., right? And you can just figure out what has the biggest probability of winning, what sort of wins can happen. You can even simulate them, maybe write a short software to see how quickly the probabilities converge. So suppose we have some game and the payoffs for that game are x1 through xk, right? With corresponding probabilities px1 through pxk. Then the expected value is what? I mean, this definition of expected value is arranging we played n games, right? We played n games. How many of those games contributed to pay off or to prize x1, right? So you understand what I do? I don't look at individual outcomes of the game, right? Let's say if I play the roulette and I put my money on red, let's say, right? I don't care which particular red number comes out, only that red came out, for instance, right? Red gives me, let's say, this amount of money. Doesn't matter. I put, let's say, $10 on 0 or $10 on, not on 0, whatever red values are available, right? I forget if red is even or odd or whatever. So, so this is the price per game, and that produced our payoff x1, and this is the payoff x2 times the number of games that produced that payoff and onwards. Yes. You look at this expression and then you sum them up. That's the average that you received per game. You understand? You played capital N, you played little n games, and the numerator represents the total amount of money that you earned. And when you divide by n, you see how much money you earned per game on average. Yes? And what happens is that if you played many games, you can take n to infinity, and you can see that this expression is simply the probability of xk. You see? We then have xj times pxj, where j is 1 to k. So this is just the probability of getting that payoff. So we have that expected value from this description is just the payoff multiplied by the probability of getting it. You see how we derive this expression? Yes, guys? Yes, Nicholas? Yes, Barry? It's very, very important for you to see it as clearly as possible and hopefully as I explained it. And then, guys, if you're interested, I try to include in the exams, I try to include problems from the actuarial exams, right? I mean, I have it over here. It's very addictive, you know. I mean, I cannot go to sleep. I just sit and I solve those questions, and I just cannot deprive this joy from you. That's how I feel, you know. You might be thinking, who in his right mind will be solving actuarial exams for fun? But that's only because you have not lived in the hell of doing research that I have to do, right? Which is worse. It's so much worse that this feels like you're playing video games. I have to really, you know, I'm ashamed, terribly ashamed that at night at 4 o'clock, I just sit and solve those questions instead of my research. Good. So, and I just want you to feel the same joy. Well, I don't know what it keeps. I also spend time arguing with Germans here and there, you know. So here we go, guys. So the expected value is in general defined to be just add up all x's multiplied by the probabilities as long as this x can occur. Yes. So let's find, for instance, the outcome of tossing a fair die, right? What's the expected value of tossing a fair die? So that would be what? That would be 1 times 1 over 6, because you can get to the number 1, you can get the number 2 times 1 over 6. And when you add those together, what do you get, guys? It's 1 over 6 times the summation from 1 to 6 of k. Yes. And that is what? What's that summation? That summation is 6 times 7 divided by 2. You know that, right? You can do that combinatorially, by the way, figure it out, right? Summation of 1 plus 2 plus 3 plus 4 all the way to plus 6 is the same as 7 times 6 divided by 2. Do I need to explain it, or you see it? Let me know, please, quickly. You see how I got 7 over 2? We can explain it combinatorially, or we can explain it the way Gauss did it when he was, what, 6 or 4-3, I don't know. Okay, I guess you don't.
I have a quick question that's kind of unrelated. Expected value is kind of similar to like the population mean when you're sampling something versus your sample mean of like what you actually get. I mean,
Well, expected value is essentially what happens to you when you do something. What happens if you run the random event as a habit continuously, right? And it shows you what on average will happen. So it's very useful in understanding, let's say, what happens if you play games of chance, right? If you play many games of chance, let's say, why do casinos make money? Because they are getting expected value per game, you understand? Their expected value is positive, so they always win. They don't always win each game, but on average, if you play many games, it's the same as if they're just taking the money from you. You understand? So imagine you have this job. Like, lottery is a great job. I wish I could run a lottery, you know? I would be a millionaire instantly if people would buy my tickets, and I would be able to pay them. Even though I don't have the money right now, if they give me the money for the lottery tickets, I'll be able to pay them because of expected value, right? Yes, but only government is allowed to run the lottery because they are, in a sense, the biggest mafia. Six. The upper bound is here you can see it's 6, and here it would be 6 times 7 over 2. Do you want to know why it's the case, guys, quickly, or you understand why the sum is 7 over 2? And we're going to try to interpret what this expected value means in a moment. But come on, guys, you look like you were frozen in the refrigerator. Well, I mean, of course we did it, but I don't know if you're aware. I mean, you might be just staring into space. All right, so what is 7/2? So how to interpret it? It means, for instance, that if you were to be paid $1, if 1 comes out, or in $2 if 2 comes out, and so on, then if you run the simulation, what happens is that if you play, let's say, 1,000,000 games, it's as if you're getting $7/2 per game. Understand? So if you play 1,000,000 games, what would you get? You will get 1,000,000 multiplied by 7/2. Right? It would be very, very close to that number. It will not be precisely that number, but it will be very, very close to that number. And the more games you play, the closer it will be to the number of games multiplied by 7/2. What else does it mean if it's not payoff, if it's not money, right? For most people, if it's not money, it doesn't mean anything. But what this means is that if you throw the die and you see, you record, okay, we have 1, outcome was 1, outcome was 2, outcome was 3. That means that on average, when you toss the die, it's as if the die always shows you 7/2. Each time you throw the die, on average, it just shows you 7/2. Yes, which is 3.5. It never ever shows you 3.5, but that's what on average it's doing. Okay, so let's consider the next game, and you will help me understand it. Yes, so suppose that I offer you the following game. No, Nicholas, it's all the way to 6. There are 6 sides to the die, correct? Die has 6 sides. Last I count, if there are different dice, but a regular die has 6 sides. 1, 2, 3, all the way to 6. Good. So it's all the way to 6, and the summation is 7/2. Now, suppose that when a fair die is to be rolled, you win 6 you win $6 if the outcome is 6, and for every other outcome you lose $1. Do you want to play the game? Right, or doesn't. Maybe you don't like the game, it's not exciting enough. And of course, imagine what I could do now is I could play very fast 1,000,000 games. Would anybody like to receive the award of me if let's say you play against me 1,000,000 games, and you know, using computer I can do that very fast, and you get the payoff. Would you want it or not?
I have a quick question. For the expected value of X, why don't we have a +6 times 1/6?
Well, it should be plus
Okay,
6 times
okay.
1/6. I just maybe that's why people were surprised, or whatever they were writing. It's plus
Okay.
6. It should not
Okay.
terminate at 5. I just saw the 1/6 over here, I guess, and maybe that's what you were what you tried to say to me. I just is that what you were saying, guys? So I said that die has 6 sides, so it should, the last number should be 6. I understood it as you saying the last number should be 5, but I think we are now on the same page. Yes, I think my poor kids have not been to a casino or something, right? All right, so yes, so how much so would you like to play this game? Well, for that we can calculate the expected value. Yes, so we know that the random variable either gives you -1 or 6. Do you agree? Either you get -$1 or 6. Now, what's the probability of getting -$1? It's 5/6, correct? 5/6. And what's the probability of getting $6? It's 1/6. Do you understand what this calculation is doing, guys? So here I played a bunch of games. 5 out of 6 of those games will be gathered together to produce -1, right? So if I play 6 games, imagine you played millions and millions of games, what you would observe that roughly for every 6 games, 5 times you lost -1 and 1 time you lost $6, but you still come up a winner, right? Although you lost 5 times $1, the one win actually compensates for everything. So what will happen is that you will get 1/6 of $1 on average every time you play the game. That's what the 1/6 means. Is it a good game for the casino or for it? It's a very good game for the casino if people want to play it. right? So this is the amount you will be getting from me if I could offer it to you, right? It would be, if you play 1,000,000 games, you would roughly be getting 1,000,000 divided by 6. Might be a different number, but it would not be very, very, very different from this, right? It would be very close to 1,000,000 over 6. Convergence will be pretty good here. Okay. Now, next question is, we are going to again look at Russian roulette. And it's played with 7 chamber revolver, and 1 bullet is in one of the chambers. On average, how long will the game be lasting? What do you think? And you can solve this question. You can, even without doing calculations, you might be able to figure it out. On average, how long will the game continue? How many rounds, right? So round, right? Until you hear the shot. Intuitively, 3.5 rounds, you think, Nicholas? Let me help you with this intuition, right? So what happens, what is the probability supposed to do, right? So what's the probability of the bullet firing? Tell me, what's the probability that the bullet is firing? 1/7, which means what? Which means you will hear a shot once every 7 rounds. So how long does the game, how long does one Russian roulette game last? How many rounds does it last on average? Very good. You see, guys, you think this way, you understand what probability is, and suddenly without doing a calculation, you already think, you're expecting that the game will last 7 rounds on average. Sometimes longer, sometimes shorter, but on average 7 rounds. And now we are going to calculate it the long way, just to verify that we are not wrong. The expected value is what? The expected value is the summation where n goes from 1 to infinity of n times 6/7 to the n-1 times 1/7. Yes? And every time I see the summation, I remember the movie The Deer Hunter with Robert De Niro, right? It's like pow pow, right? Where they are prisoners of war and they're forced to play Russian roulette. You should watch the movie; it's pretty good. What's the name of the other guy in that place there? Come on, guys! Somebody knows the movie, correct? Somebody watches good movies, right? Not just garbage. Walken, very good. Yes, Walken. Yes, Christopher Walken is playing there. He's a good actor. Yeah. So let's solve this carefully, guys. So how do you solve this? Well, do I need to explain how to sum it up, guys, or you can figure it out? You know how to carry the summation. You know geometric series, correct? And I think I taught you how to. We even made a pause. We reviewed how to sum up a series of the form n times x to the n-1, right? So I need to understand how to sum those series. Again, what it is, it's n-1 times x to the n-1 plus x to the n-1. And that's the summation of n-1 times x to the n-1 plus the geometric series, which is just 1/1 minus x. Yes? And then what can I do with this expression? I can make it look like that. You agree? At 0, when n is 1, it's 0, so it doesn't matter. So I just readjust it. It's m x to the m, and then I can factor out the x, and that's m x to the n-1, and that again is h. So it's x times h plus 1/1 minus x. So you see what we have? H is equal to x times h plus 1/1 minus x. And when you solve it, h is equal to 1/1 minus x squared. If you're preparing for the actual exams, guys, you need to know those things very fast and rapidly, right? They ask very complicated questions, right? Tricky questions. You need to answer them quickly. You need to carry often many calculations or somehow go around them. Yeah. So what does it help us now with? So what do we get? In our calculation, that means that the expected value is 1 over 7 multiplied by 1 over 1 minus 6 over 7 squared. And when I multiply and simplify, I get 7, just as we expected. Good? And now we come to a very interesting question. Have you all heard of St. Petersburg's paradox? No? Well, then I'm glad to be the first to tell you about it. Okay. So here is a game that you're offered. Suppose you come to a casino and they tell you the following. They tell you, we're going to toss a coin. It's a fair coin. And if the coin comes up heads on the first roll, you get 2 to the power of $1. If it comes heads first time on the second roll, you get 2 to the second dollars, right? And then 2 to the third and onwards, you understand? So the longer the coin avoids coming up heads, the longer the game lasts and the bigger is your prize. Yes? Would you wager $1 million to play this game? That's the question. And I mean, I know some of you don't have $1 million, and imagine that what you can do is you can take credit, right? You only have to pay the bank once you quit the game. You only have to pay the casino once you leave. Make sense? So you can play one round and then you can play another round. Each round, each game will cost you $1 million. Make sense? So it's very difficult to, of course, solve it right away or figure it right away if that's the first time you hear about it. But what do you think? Let's see if you can consider this question. What do you think? The game, the particular game is over, but then you can pay additional $1 million to play another game. You understand? Each game costs $1 million, but you only have to pay once you leave the casino. So let's say you got heads on the third roll. So what do you get? You get $8. You have to pay $1 million. You get your 8, and you can decide, okay, I don't want to lose $1 million, so I'm going to play another game. So I'm going to wager another $1 million. Yes? Would you play this game? Why or why not? You've seen the social experiment, right? Where you go on the street and you offer people, let's say, a brick of silver or a brick of gold, and it's real. And they just don't, and they say, you can take this or you can take candy or Snickers or something, right? And usually they don't want any of it because they don't trust. Maybe that's my interpretation. They just don't trust. So the question is, you see here, all the cards are on the table. There is nothing more other than what is written here. Why would you like to play it, or why would you not like to play it? And not because, I mean, I'm assuming you all like to win money. Doesn't matter. Let's pretend that you do, right? If it's not your goal. Which series converges to 0, Gustavo? Kind of. Well, okay, that's interesting. That's interesting. All right, so some of you are pretty quickly on an interesting track. Okay, so let's analyze it together. Yes, guys. So the probability that on a particular round, of course, it converges to 0. I mean, but let's be careful here. So what random variable are we going to use? Well, you are always paying 10 to the 6, so I want to know what's your net win, right? So it's 2 to the power of 1 minus 10 to the 6, or 2 to the power of 2 minus 10 to the 6. That's your net gain. Good. And what's the expected value of that? Well, the expected value of it is 2 to the n minus 10 to the 6 times 1/2 to the n. And when you distribute the 1/2 to the n, what do you get? You get 1 minus 10 to the 6 over 2 to the n. And then if I partition it into a partial sum, this is the summation of ones minus a geometric series, right? This geometric series is just a finite number, whereas this is going to infinity. So what is this saying? It says that your expected value is infinity. Do you understand what that means? Will anybody tell me what expected value equal to infinity is? Tell me. It tells me. No, Ryder, that's not what it says. I mean, maybe that would be true what you're saying, but the expected value is saying what? It says that as I play more and more games, right? If I play many, many games, the average is going to grow larger and larger and larger, right? I mean, yes, I mean, if you to get infinity, you have to play infinity many games, perhaps, but the average will just be growing, right? So if you play 1 billion games, 1 trillion games, a quadrillion games, your average per game is just going to be larger and larger and larger, reaching infinity potentially, right? That means that play enough games and you win a lot of money. Even each time you wager 1 million, it will be offset by your huge winnings in the long run. Do you want to play the game now? You see, I mean, the infinity only means this: play many, many games, win a very, very big prize. Play infinitely many games, win infinite prize. But you know, you don't need to stay forever. Just win. Just play until you get filthy rich, and then you can leave. Yes, Gustavo. Not only you. Let's try to understand what happens to this paradox. Or maybe we will. Do you want to do you want to listen to it, or do you want to stop? We're almost at the end of the lesson. So vote, guys, if you would like to finish the paradox, or if you'd like to go and rest. Okay, well, Ryder, you're getting it. Yeah, so I will finish it, and if you cannot stay here and want to leave, then good luck on your next class and rest. Okay, so here is how I thought of it. So let's modify this paradox. All right, modify this paradox, and let's not allow you to win $1 million. Let's suppose the maximum tosses is going to be capital N. Let's truncate it, right? Which means that if it works just as before until I reach 2 to the power of capital N, and if I don't get heads after that, I get 2 to the power of n plus 1. That's how I decided to do it, right? You understand what I'm saying? Yes. So this is how much you win. So it doesn't grow forever, right? It will not wait. If let's say if capital N is 10. After 10 tosses, I'm not waiting anymore. I will just give you 2 to the power of 11, right? Dollars. We'll stop the game. Yes. What are you going to gain from that game? Would you pay $1 million? So how large must capital N be for you to win? To come up a winner, right? So then when you calculate it for that capital N, you get this expression. And then you translate to that equation. It means that N has to be, for you to be coming up to win at least, for this to be more or equal to $1. Right, before that, it will be n plus 2 minus 10 to the 6. I mean, if 0 means you're neither winning nor losing. So you want it to be, it's always an integer, so you want it to be bigger than or equal to $1. That means that you have to allow capital N to be bigger than or equal to 10 to the power of 6 minus 1. Yes? Which means what? Which means the game is not profitable unless you allow the coin to roll a fair coin to produce about 1 million tails before producing the first head, right? A fair coin will have to produce 1 million tails before producing the first head. What's the likelihood of that? Well, so you try to compare for it, guys. In the entire universe is supposed to be, it supposedly has 10 to the power of 82 atoms. So if I count, forget about planets, galaxies, or anything, you see, 10 to the power of 82 atoms. Now, 2 to the power of 10 to the 6 minus 1, you can see I make the calculation, it's bigger than 10 to the power of 200,000. So that means that you would have to wait universes upon universes, right? Coming and going. Right, I'm not sure even a number that I completely do not comprehend before you see this $1 payoff, right? So it's just too long to wait, unfortunately. So your salary will be just you would be the most severely underpaid person per hour, right? So that's why you probably don't want to play this particular casino. No, not that many games. No, that would be nice. You would have to wait. You would have to wait 10 to the power of that games. You understand? 10 to the power of that games. That's not so much. 10 to the power of that games is an astronomically large number. So large that it's many times. It's many. If each universe were an atom, it's many more times. You can build many universes out of it. You understand? You can build something incomprehensible. If all the universe were just one atom, you could have constructed out of those universes more universes than you can count, right? So you understand? I mean, I do not have a sense of how huge that number is. It's insanely huge. Right, so that's the problem. You would really have to be patient, and yes. So, guys, thank you for your attention, and goodbye. If you want to go, I'll see you on Wednesday. We're going to do a lot of expected value. Have a good weekend. No. I mean, it's Monday, correct? You're not running away from me. So today's Monday. I'm not going crazy. Yes, it's not Wednesday. It's Monday. So no, I mean, we're going to meet before. Take care, guys.